Hello everyone, my name is Niranjana Sankaran. I will be walking you all through human factors in AI product management for my use case, payer plan mapping using machine learning. This is a healthcare revenue cycle management use case. Let's get right in. Here is the problem statement. Healthcare systems must map client specific payer plan IDs to standardized identifiers in order to automate RCM functionalities that are otherwise manually done. But mapping is not straightforward because payer names vary wildly across systems. Example United Healthcare, UHC, and United Healthcare. They all mean the same, but they are spelled very differently. Plan codes, clearinghouse IDs, and formats are inconsistent across sources. The current state is very manual mapping using spreadsheets and rule based crosswalks. It depends on tribal knowledge, no institutional memory. It's not very scalable, and mapping needs to be done manually for every new client and payers. There is no learning from past decisions because each mapping starts from scratch. Here are the impacts of incorrect mappings. Unable to perform RCM functionalities like eligibility checks and claim statusing, misrouted transactions and increased manual work, delayed revenue realization due to the inability to automate, as well as longer time taken to perform RCM workflows, which leads to increased operational costs and poor user experience for operations teams. We established earlier that ML could help solve this problem by walking through the CRISP DM framework. We now want to ensure that we are accounting for the human factors while using ML to solve this business problem. Now let's break down the tasks involved in the current mapping exercise, which is very manual. We can see the various tasks involving with mapping and their corresponding pain points. Task 1 is identifying unmapped payer plan. Operator sees a new or unrecognized payer plan entry. Unfortunately, there is no proactive detection today. It's discovered only when the operator comes across an unmapped payer. Step number 2 is search for matches. Operators manually search spreadsheets, crosswalk tables, payer portals, or they ask their colleagues. Sometimes they may even need to talk with payers in order to help identify matches. This step is very time consuming. It depends on tribal knowledge and there is no ranked suggestions provided by the system. Step 3 is evaluating candidates. Operators compare payer names, payer IDs, plan codes visually. There is trial and error involved in identifying the mapping. This evaluation is very subjective to judgment. There is no confidence signal provided by the system and it's inconsistent across operators. Next step is for the operator to document the mapping that they have identified. They enter the mapping into the system. There is no audit trail of why a mapping was chosen. If it is documented, it's not very search friendly for future consumers. Step 5 is validation. Whether the mapping is correct or not is confirmed only downstream when we get a success or a failure from the transaction execution. This delayed feedback leads to compounding errors silently. Here are the key insights we can infer from these tasks. Step 1 can be made proactive. Instead of waiting for the operator to come across unmapped payers, ML can run its mapping as new payers are added to the system. Steps 2 and 3 are the bottleneck. Searching and evaluating candidates is where most time is spent and where most errors are introduced. ML can directly accelerate these steps by generating ranked candidates with confidence scores. Step 4. Mapping is subjective to the operator that's performing it. Since there is no audit trail on the who and the why, errors with mapping are not caught until manual reviews are conducted or transactions fail. Step 5. Feedback is delayed. Feedback is not obtained until the transaction success or failure is observed at a later point by the user. This delayed feedback leads to compounding errors. Now let's take a look at the proposed user design that is interactive. This user experience design is based on the principle of using ML as a decision support tool with the human operator always remaining in control. That is, no mapping is ever auto committed. It proposes to reduce the workflow from 5 steps to 2 steps for the manual operator. Step number 1, operator reviews the work queues that surfaces up the suggestions along with the evidence and confidence scores provided by ML. Step 2, operator accepts, overrides, or escalates to the recommendation provided by the ML. This eliminates manual search and subjective decision making. Some of the AI specific considerations that have been taken into account in order to promote the human factors are user inputs and feedback loops for continued learning and tuning of the machine learning model. By taking into account every accept, override, or escalation from the manual operator and by the downstream transaction's failure or success. Transparency. By showcasing evidences and prior transaction success count for the suggested values and by displaying machine learning models information. Communicating uncertainty by displaying the confidence scores and by not forcing a suggestion when no sufficient match is found. Here is the prototype. As you can see, it shows the suggestions, confidence scores, and promotes user inputs and feedback. Next, let's look at possible privacy concerns, what laws would be applicable for this use case, and what we need to do to mitigate concerns. Since insurance payers and plans are not patient data, they do not pose a PHI exposure risk by themselves. But when used as a part of RCM workflows, they could lead to accidental exposure. Claims and eligibility data and transaction outcomes have patient names, date of service, diagnosis codes, clinical and treatment information. Operator activity logs could be used for performance surveillance without appropriate governance in place. Client specific configurations are proprietary business data. So, training data needs to be secured since it may touch patient, PHI, PII, operator logs, as well as client specific configurations. Next, let's look at the laws that are applicable. HIPAA and state privacy laws like CCPA and CPRA are applicable. We need to implement the below to ensure that we are in compliance with the laws. De-identification. Patient level identifiers need to be stripped before data enters the machine learning pipeline. Role-based access control. Operators should only be able to see the mappings for their designated clients, aka provider health systems. Audit logging. All data access, training runs, and decisions should be logged for audit trail purposes. Data minimization. Collect only the minimum necessary data and provide the consumers, patients, the ability to know, delete, or opt out of the data collection process. Encrypt the data when it is at rest as well as when it is at transit. Business associate agreements need to be in place. They govern all client data sharing. Let's look at ethical considerations. Here are some of the biases that are applicable to this use case. Popularity or representation bias for payers. Model trained on high volume payers perform better for larger payers, whereas they play worse on smaller or regional plans and payers. Smaller payers get lower accuracy, leading to operators having to do more manual work to identify the mapping for smaller payers. Popularity representation bias for provider health systems. Training data could be skewed towards larger health systems, so new or underrepresented health systems experience degraded performance. Operator confirmation bias. If operators feel comfortable with the recommendations that machine learning model is making, they may not review every single recommendations. They may choose to simply accept the recommendation provided by the ML. Then the model becomes overconfident on its own mistakes, errors compound. Historical labeling bias. Past mapping decisions reflect outdated conventions or individual preferences. Then model will learn and perpetuate historical inconsistencies. Geographic or demographic bias. If there are payers that are serving specific vulnerable populations limited to specific geographic locations, and if they are not represented in the training dataset, the performance of the model will be not up to par for those payers. Here are a few steps we can take to make sure that AI is fair, accountable, and transparent with this use case. For fairness, sampling strategies to adequately represent various payers and health system types and sizes. Uniform confidence thresholds and escalation pathways in the user experience design. Reviews when accuracies for any of these segments drop below the set threshold. For accountability, human in the loop with every mapping requiring human oversight and confirmation. Full audit trail. Model governance for retraining, testing, and rolling back the model if needed. Ownerships are established for operations, data science, and product management for clear accountability. For transparency, system should clearly show evidences and confidence scores for its recommendations. Then clear documentation of the data that's being collected, how the data is going to be used, training data, known limitations, guardrails, and performance. Stakeholders should be communicated about ML usage, data protection practices, and human oversight model. We covered these four areas because building an ML product isn't just about the model. It's about understanding the problem, designing for trust, protecting the data, and ensuring fairness. That's what separates a prototype from a product. ML presents a scalable and high impact solution for payer planning mapping when paired with thoughtful UX design, strong privacy governance, ethical safeguards, and human in the loop controls. Thank you for listening to my presentation.